Okay, guys, so I'm going to go over a brief review of our 5 questions that I got graded. So your graph should look something like this here at sea level. It was 15 degrees Celsius, and then as we come up through the troposphere, our first one, we end up hitting this pause right here, right? We call this a pause because the temperature has went up as we go up in elevation, the temperature has stayed constant, right? If this is our altitude over here and this is our temperature, right? Our temperature has stayed constant as our altitude or our height has gone up. And then we run into another pause, a temperature pause right here, and it's a little zone. And so this is our stratopause. So we have our tropopause. So troposphere, right above our troposphere is our tropopause. Our temperature is pausing. Then our stratosphere ozone layers right here. And then right above the stratosphere is our stratopause. And then our last one right here, our temperature pauses again, is our mesopause. So the mesopause will be directly over the mesosphere. And then above the mesopause is our thermosphere. And so we see number one, it says, what's the basis for dividing the atmosphere into 4 layers? 1, 2, 3, and 4. So we divide these in how the temperature changes. So every time as we go up, we're cooling down. That's a troposphere. The next layer, as we go up, we heat up. The next layer, as we go up, we cool down. As we go up, we heat up, right? So it's because of the changing temperatures. This is how we divide them into 4 atmospheres. Now, if we look here at the troposphere, as I go up in the troposphere, so does it increase or decrease in altitude? Does temperature increase or decrease with the altitude? So in the troposphere, as we go up in altitude, the temperature decreases. It goes down. The stratosphere, as we go up, it increases. Mesosphere right here, as we go up here, this is our mesosphere. As we go up, it cools down. As we go to our thermosphere, as we go up in altitude, it heats back up. Okay, so then it says where about is our height, where's our temperature. So our tropopause, you could have put anywhere between 12 and 20 kilometers. And the temperature of that is about 56 degrees. That's what it says on your table. Your stratopause right here, it's about 48 to 52-ish is our stratopause, and the temperature is about -2 degrees. And then our other one is like 85 to 92 or something like that in kilometers. Our mesopause is that, and it's about -86 degrees Celsius. Okay, so then we get down here to number 4. What causes the temperature to increase with height in the stratosphere? So right here, why are we increasing? Well, if you guys remember, we wrote the other day, we talked about the ozone layer, this warming. So the temperature begins to increase with altitude in the stratosphere. The warming is caused by a form of oxygen called ozone, the absorbing ultraviolet radiation by the sun. Bam. So there's the first part to that one. And then it says, why does it decrease in height with the mesosphere? So if we come back here, the mesosphere, the overlying mesosphere does not absorb solar radiation, so the temperature decreases with altitude. There's your second part to that one. Number 5 then says, what causes the temperature to decrease with height in the troposphere? And so we know that the troposphere is at the sea level, right, where we live, is the absolute warmest part of our atmosphere. However, it cools down as we go up in the atmosphere. So why is that? Well, if we remember back here, the temperature variation, blah, 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 right here. The Earth's surface is the primary absorber of solar energy. Some of this energy is re-radiated by the Earth as heat, which warms the overlying troposphere. So what's going on is while we're right close to the surface, as we get further and further away, that energy dissipates. We don't feel it as much, so it cools down as we get further and further away from that energy that's being given off by the surface of the Earth. Okay, and so that's our quick review on our homework. Next, so let's get into our, we don't need that. Okay. So the next thing, all right, so sorry about that. I had to pull up another document. So here's what we worked on yesterday, the Earth's energy budget. And so we talked about you get a paycheck from your employer, whoever, you get $174 to spend, and you can't spend any more or less, okay? And so you spend it in ways like 6%, 20%, 19% here. Is being reflected by the atmosphere, is being reflected by the clouds, being reflected by the Earth's surface. Well, then some of it's absorbed here by the atmosphere before it gets to the surface of the Earth, and then the rest of it gets absorbed by the Earth, right? And then we calculate what's the output. So if we're inputting 174 petawatts into the Earth, that's hitting the very tip top of the layers first before it makes it to the surface, then we should be getting 174 out, right? That's if we want to keep the temperature consistent, the global temperature consistent. But we know that that's not happening. Our temperature's always fluctuating. We're always going through climate changes, as in we have gone through multiple ice ages. We've gone through multiple warming periods, right? And so if we're getting 174 petawatts, but then we're giving out 170 petawatts, that means we're holding on to an extra 4 petawatts. And therefore, if we're holding on to more energy, maybe because our atmosphere is absorbing more energy, so there's more greenhouse gases like carbon dioxide, methane, maybe our atmosphere is absorbing more energy. That means that we're holding on to that energy. Therefore, we're going to warm up as a globe. Now, if we're giving away more energy than we're taking in, right? Let's say we're taking 100, we're giving away 180 petawatts. Now we're giving away more than that we're actually getting. So now our energy, maybe the atmosphere is reflecting more. The surface is not absorbing as much. The atmosphere is not absorbing as much. Therefore, we're going to cool down and we're going to enter a cooling period in the Earth, as in like an ice age of some sorts. Okay, there's a video that you guys can watch. It's a very helpful video right here, the Earth's energy budget. That's kind of a 4-minute deal that talks about this. We did a demonstration with a yoga ball and the flashlight. And so we'll kind of talk about this, discuss the tilt of the Earth. So what's the reasons for the seasons and things like that. We did not get to these videos, so I'll get these videos replaced. And so what we did was we just finished the rest of the Earth's packet, and then I have this complete, the worksheet attached. It's over sections 1 and 2. So let's go ahead and finish up the Earth's energy budget, or the reason why we have the seasons and uneven heating. Okay. So a lot of you guys, I've already got a couple emails from you, and so I just kind of want to clarify what's going on here. So at the equator, we know that it's nice and warm here at the equator. Look at this. My cool little, let me see. Got my little, I don't even know what I call this thing, my model. Okay. So this is my sun. This is the Earth, right? And we know that the sun is giving off radiation, and it hits the middle of the Earth directly, right? And it will always hit the middle of the Earth right around the equator the most directly and give it the most energy, therefore making it the warmest. And so as we get up further and further towards the pole, the poles receive less of that energy, right? If I start here and I go downwards, it receives less of that energy. And so now you can kind of see a tilt of our equator, right? Our equator is not flat across, it's tilting. And so right now it appears that here's North America right here. It's tilting towards the sun. So therefore, as it's more tilted, the equator is pointing down just a little bit. So now the Earth, the Northern Hemisphere, is receiving the most direct sunlight. Therefore, that's why we warm up during the summer. And now the sun is actually present for more days, so we get more sunlight. Our days are longer in terms of sunlight. And then if it comes all the way around, it comes around. All right, so now, there we go. Okay, so now the Southern Hemisphere, right? So now our equator's pointing away, and this guy, and our tilt's always facing the same direction as well. It's not going to change direction. So if we see it over here, it's still pointing in this in this direction. And if we go over here, it is now pointed in the same direction, in that upwards direction. Okay, and so our Southern Hemisphere now is exposing itself more to the sun. Okay, so now this guy's, the Southern Hemisphere is in its summer, and then the winter is taking over here in the Northern Hemisphere. So let's talk a little bit more about that. Okay. So if we take a look right here, it says the curvature of the Earth changes the angle at which the solar radiation hits the surface. So if we see right here, it talks about the Earth's perpendicular to the surface at noon. So that means that as this direct ray of sunlight comes in and smack, it hits the equator here, it's hitting it at a very direct angle and making it at a 90-degree angle or a perpendicular angle. Then if we come up towards like where we live, we're about 40 degrees, 45 degrees north of the equator. we see that there's a slight angle. So you can think about this as if you're shooting a bullet or something like this. And if it hits a flat target, it will punch through that flat target or it will hit that, right? And it really doesn't bounce away. If we come up here and we're hitting the curvature of the Earth now, we're not hitting it so directly. So now this bullet is coming in. It's about to hit. If this bullet is a light beam, right, as it hits this curved surface or this angled surface, it has a much better chance of hitting it and skipping off and reflecting, okay? The bullet is being deflected off of the surface. So it's not taking that direct impact where now this angle is right here and it's being kicked off like that. Another way that it could kind of be summed up, I have this flashlight here, and I don't know how well you guys will be able to see this. All right, so you can see it. So right now, I have this flashlight. It's pointing directly at it. So this is a direct beam that's pointing here at like the equator. But then if we can imagine this wall is now going to bend backwards, bend away from us like a sphere, right? So now we're going to imagine that this wall is going to be more like a sphere. And so what's going to happen to our ray of light is right now it's taking up this much space, but then if I tilt it just a little bit, now you can see this ring a little bit better, but this ring is now covering a much larger surface area than when it was directly being shined against the wall. So now as we get away from our equator, we're causing the surface area that this light covers, this light is covering now a larger surface area than what it was when, boom, right here. And the thing to remember is this flashlight is putting out the same amount of energy. And so the same amount of energy is being on the equator is being focused into a smaller surface area. Whereas we get up to the poles, that same amount of energy is now being spread out over the farther and farther we get away, a larger and larger surface area. So like I was explaining it to kids in class today, if you have $100 and you gave it to a small group of people, like 2 people, you can give $50 a piece to those 2 people, and that's going to go farther. That's going to help them out more. Or you could give it to a larger group of people, let's say 100 people. And so now 100 people each get $1, and that $1 will not go as far for those 100 people as $50 would for those 2 people. So let's see, the outside the tropics. So we start talking about the Tropic of Cancer and Capricorn, which we'll come to the next page. But the biggest thing here is we have direct rays of sunlight. It's more concentrated here, therefore more energy is hitting this and is being absorbed by the surface of the Earth. Where if we come in here, we hit this curved, angled surface, and now more of it's being reflected and reflected. It also has to travel through a little bit more atmosphere. And here, here's my picture. Okay, so if I show you this picture, let's see. Can you guys see me? I don't know if you can see me. But anyways, here's our picture of the sun, and we're getting solar radiation. This blue, between the blue and the green, is the atmosphere, and then the green line is the Earth's surface. And so we have the equator right here. So first, we see the solar energy is the most concentrated. It's hitting it directly. Less atmosphere to travel through. So here, it's going straight through the atmosphere. Up here, the solar energy, again, is hitting this, and it's spreading over more surface area with that same amount of energy. But then we also run into, there's more atmosphere, plain and simple, to travel through that now that we're traveling at it through an angle. And so there's a greater chance of that energy to being reflected. So there's a greater chance of reflection happening because of atmospheric conditions, because of clouds and things like that. And then we can even have some energy that travels parallel to the poles here, where we have ice caps. So this energy is passing through our atmosphere, but it may not come into contact with the surface of the Earth. Therefore, it's not warming our troposphere, where most of that weather is happening. A lot where weather does happen is in the troposphere. So anyways, there's that. You guys can read this stuff on your own, but number 2, describe the relationship between the curvature of the Earth and the amount of solar energy received at the surface. Well, as that light hits a curved surface, like I said, it tends to spread out more and more. That's really number 2. Explain how this affects the climate at both points. Well, here at the equator, again, we have this direct rays that's boom. It's still hitting, obviously, a sphere is going to have the same curvature all the way around. But if we have this, the sun is obviously over here. It's not up, it's not up here in the corner. It's not down here below, but it's right over here, and it's shining direct rays. And so the curvature of the Earth is not going to affect it as much because it's right here directly shining upon. But then as it gets farther and farther out, or like I said, south of the equator, north of the equator, it begins to spread out more. And so the equator, Earth's energy, or sorry, the sun's energy is I can't talk. I'm sorry. The solar energy is more concentrated on a smaller surface area, so it gets more energy. Here at the poles, the solar energy is spread out more over a larger surface area. There we go. That's what I wanted to say. Okay, now let's talk about the Tropic of Cancer and Tropic of Capricorn. So here's our Tropic of Capricorn. It's the northern latitude. This guy's actually 23.5 degrees north, while the Tropic of Cancer is 23.5 degrees south. So why is that? Well, that's actually talking about, if I come back here to my model. Okay, so you can barely see it, but there's something called the winter and the summer solstice. And so our summer solstice is when the northern hemisphere, our northern hemisphere on June 20th is the day that our northern hemisphere is tilted the most towards the sun. And so at noon, if you're standing on the Tropic of Cancer, okay, if you're standing on the Tropic of Cancer, that means the sun is going to be directly overhead, and that part on the Earth at that moment is receiving the most direct sun rays. Okay, and then as we go farther and farther south of that, or north of that point, that those sun rays are going to spread out more and more and more, giving less energy per square unit of area. Okay, and then if a year goes round, now our northern hemisphere is facing away, our southern hemisphere is getting the most. So now if it's December 20th, which is the winter solstice, now the Tropic of Capricorn here is 23.5 degrees south, and at noon on that day it's going to receive the most solar energy out of any point on the Earth, the most energy. And so why 23.5 degrees south? Well, that's the tilt of our axis. It's 23.5 degrees. Okay, let's get this a little smaller again. So you guys can kind of read this. It says 23.4, pretty close to 23.5. And so we see these direct solar rays. So you can see this on the Tropic of Capricorn here. It's a little funny because on my other model it says opposite, so I'll have to check that out. It says the Tropic of Capricorn is down here and the Tropic of Cancer is up here. Anywho. So this is our summer over here on the left side. This is where, so you can see the southern part of Florida, mid-Mexico here is on the summer solstice is actually getting the most sunlight. But the reason why we call this the Tropic of Capricorn and the Tropic of Cancer is because the sun through the 365 days moves and covers all of this area every single day for 365 years. So this area between the Tropic of Capricorn and the Tropic of Cancer is receiving that direct sunlight all 365 days, but it's just bouncing back and forth all of those days. Okay. And so we can see that in the winter solstice, so this is December 30th or 20th, this is our shortest day of the year. We receive the least amount of sunlight, and that's because as the sun comes up, it barely comes up over the horizon, and then it goes right back down on the west side, right? Then as we get into summer, the summer solstice, now during the summer, as we go from winter to summer, that every single day the sun rises farther and farther above the southern horizon. And then on our summer solstice, it gets the highest point it will in the sky, so it will never ever get straight over top of us because we're not low enough in latitude. And so our summer solstice gives us a short shadow. Okay, so that's how we can see that we're getting very direct rays of sunlight because of our shorter shadow that we're getting. But then during the winter, again, more of that solar energy is being spread out, and we can see that through here with a long shadow here in the winter. And so what causes the changes of the seasons on Earth? It's just the tilt of the Earth at 23.5 degrees, and then us revolving around with that. So then the northern hemisphere is not always facing that way. It's always facing the same direction. And so when it goes on the exact opposite side, now it's facing away from the sun, and now it's in winter. What effect does the change of the seasons have on the angle of the sun above the horizon at noon? Well, like I said right here, above the horizon, in our winter solstice, it's very, very close to the southern horizon. And then during the summer solstice, this is the farthest point above the southern horizon. All right, when I talk about the horizon, I mean when you look out over a field, right, you just see the horizon where the land meets the sky. And so if you're looking south towards the equator, right, that's what I'm talking about. And so we see that sun come up further and further every single day until our summer solstice, and then after summer solstice, it then goes down again. Compare the length of the shadow at noon in the summer and at winter, and we just said it. During the summer, our shadow at noon is going to be very short, and in winter, since it's closer to if we're thinking about this as the horizon, it's closer to the horizon, therefore it's got a lower angle, therefore it's going to make your shadow much, much longer. Okay, so the homework for today is right here. Earth's atmosphere, which we've talked about, and now energy transfer in the atmosphere. Now, this is in your book, so I also attached a reading right here. So you have section 1 that you can go through. It talks about the makeup of the atmosphere, right? Here's our gases in the atmosphere. Here's the layers, the lower layers it talks about a little bit. Here's some good graphics here, some good graphics. It does talk about the ionosphere. We haven't talked about this, at least yet, in our layers of the atmosphere, talking about this is where radio waves travel. On this side, we're able to listen to the radio. Atmospheric pressure, we talked a little bit about that when we inverted that cup with the cardboard over the top. Let's see, keep going. Here's another graph of the exosphere. So there's another guy that's going to be on your homework that we have not talked about, but it talks about the temperature in the atmosphere. Ozone layer, the CFCs, chlorofluorocarbons, that was taking away the ozone layers and causing holes. And then here's section 2, so energy transfer in the atmosphere. And so this is going to get a little more talking about the Earth's energy budget, how is energy moved throughout Earth and the atmosphere and stuff like that. And so we really didn't. So this is why I'm giving you this reading, because there's going to be some stuff that I didn't directly mention in my lesson today. So I got this here for you to do this homework here. So you have 2 sides to it. This backside over the atmosphere, honestly, like I said, ionosphere, that's where your radio waves are. Exosphere, that's that highest, most one. So process of elimination, you should be able to figure these guys out. All right, let me know if you need help. Bye.